Welcome back, everyone. Last time on our deep dive into dynamic topology, we uncovered something pretty incredible, that in the world of math, infinities actually come in different sizes. We were left with the most fundamental building blocks you can imagine, just sets, which are really nothing more than collections of points.
But that's all they are, kind of like a pile of mathematical dust. So the huge question for today is, how do we breathe life into that? How do we take a simple, boring collection of points and give it shape, give it structure, and even a sense of what it means for things to be near each other? In other words, how does a set become a space? So let's get into it. Here's our blueprint for today's construction project. We're going to start by making that leap from a set to a space. Then we'll lay down the fundamental rules of the game. After that, we'll see how we can tell points apart, and we'll discover this amazing emergent property called compactness. And we'll wrap it all up by finding a really beautiful, surprising connection between all these ideas. All right, first things first. At its core, a set is really just a bag of elements. It doesn't have any built-in geometry. Think about it. The set of all the real numbers doesn't automatically know that the number 2 is closer to 3 than it is to, say, 3 million. We have to add that structure ourselves, and that's exactly what topology is all about.
And this analogy just nails it. A pile of bricks is, well, it's just a pile. But if you give an architect a blueprint, those very same bricks can become a house or a bridge or a skyscraper. Topology is that architectural plan for our sets of points.
So what does this amazing blueprint actually look like? It's surprisingly simple, and honestly, that's what makes it so incredibly powerful. The whole rich, complex world of topology is built on just a handful of really elegant rules. Let's take a look at the axioms of a topological space. So here's the absolute key. This is how we build the structure. We take our big set of points, which we'll call X, and then we go through it and we simply choose some of its subsets, and we just declare them to be open. This special collection of subsets we've chosen is the entire structure. But of course, that brings up the question, what are the rules for choosing? We can't just pick any old subsets we want.
Well, it turns out they just have to follow 3 simple rules. First, the entire space itself, X, and the empty set have to be in our collection of open sets. That's non-negotiable. Second, if you take any number of your open sets, even an infinite number of them, and you merge them all together, the result has to be an open set too. And third, if you take a finite number of open sets and find only the parts where they overlap, that intersection must also be open. That's it. Any collection of subsets that follows those 3 rules defines a totally valid topological space.
Okay, so let's see what we've built. We've created a space, but is it anything like the spaces we're used to? For example, can we actually tell points apart from each other? With rules this abstract, that's not something we can take for granted. This gets us to the idea of separation.
And this leads to a really fundamental question. If you pick any 2 different points in this new space we've made, can I always find an open set that contains the first point and a totally separate open set that contains the second one, in a way that those 2 open sets don't overlap at all? Can I build a little conceptual wall between them? Well, the answer depends on the space. Think of it like resolution. In some topological spaces, let's call them low-res, you can actually have 2 distinct points that are kind of fuzzy, topologically speaking. Every open neighborhood you try to draw around one point accidentally includes the other. But in a higher-res space, which we call a Hausdorff space, everything is in sharp focus. You are absolutely guaranteed to be able to find 2 separate, non-overlapping open sets for any 2 distinct points. Most of the spaces we deal with in everyday life are Hausdorff spaces. Okay, so we've got our rules, we've got our separation properties, and now, this is where the magic really starts to happen. We're about to see how these simple axioms give rise to these deep emergent properties, kind of like superpowers that our space gets for free. And the first big one is the powerful concept of compactness. So, let's look at one way to get a handle on what finiteness might mean in a space that could be infinite. It's called the Bolzano-Viatris property. Basically, it says that if you pick an infinite number of points from your space, they can't all just fly off to the corners of the universe, away from each other. At least some of them have to bunch up or cluster around some point that's also in the space. And we call that point a limit point.
Now for the big one, the classic textbook definition of compactness. Imagine you want to cover your entire space using only your open sets. It's like you're trying to cover a map with Post-it notes. Now you're allowed to use an infinite number of these open set Post-it notes. A space is called compact if, no matter which infinite collection of open sets you use to cover it, You can always go back and find a finite handful of them from your original pile that still gets the job done. It's this incredible kind of mathematical efficiency. So now we've got these two ideas, right? And they're both trying to capture some notion of being bounded or contained. The Bolzano-Weierstrass property looks at infinite sets of points and guarantees they have to cluster. Compactness, on the other hand, looks at infinite coverings by open sets and guarantees that a finite number is always enough. So, are these two ideas related?
Oh, absolutely. And here's the first part of that connection, a major theorem in topology. It turns out that any set that is compact must also have the Bolzano-Weierstrass property. So if you've got that finite post-it note property, you are guaranteed to also have the infinite points must cluster property. The logic flows one way.
But the big question is, does it flow the other way? Does having the Bolzano-Weierstrass property mean a set must be compact? And this question brings us to the grand finale of our architectural plan for today, a beautiful and really surprising connection known as the Borel theorem. As it turns out, that connection isn't always a two-way street. But if we add a couple of extra good behavior conditions to our space, things that topologists call properties like T1 and perfect separability, then something really remarkable happens. And this is it, the Borel theorem. It says that in these nice, well-behaved spaces, the reverse is also true. Every set with that Bolzano-Weierstrass property is also compact. The two concepts become completely equivalent. They're just two different ways of describing the exact same deep structural property of the space.
I mean, let's just take a second to appreciate that. We started with literally nothing but a pile of points. We added three incredibly simple rules about what we're allowed to call an open set. And from that tiny seed, this profound, elegant, and beautiful equivalence just emerged. This is the real power and beauty of building mathematical structures from the ground up.
So, we've built our stage. We understand its fundamental laws, its properties, but so far everything has been static. The obvious next question is, what can we do here? What happens when we introduce functions that can stretch and bend and map these spaces onto each other? Well, that is the beginning of dynamic topology, and that's exactly where we're headed next. See you then.